In the last video, we developed a quick methodology to finding vertical asymptotes for rational functions. Let's apply that method to this particular function and see what happens. We start by finding the domain of the function. It should be pretty clear that 2 is the only value that makes the bottom equal to 0. So our domain is all real numbers except for 2. And the test for vertical asymptotes told us to plug in 2 into our function and see if we get the undefined form. So plug in 2, we get 4 minus 4 over 0, which is 0 over 0. Notice this is not an undefined form. This is something we call the indeterminate form. And this is a drastically different situation than a non-zero number over 0. Right? Recall that a rational function is just a polynomial divided by a polynomial. And by plugging in 2, we got 0 in both of these polynomials. So the factor theorem tells us that x minus 2 must be a factor of both the top and the bottom. So because we got a 0 over 0 when we plugged in 2, this function must be reducible. Let's take a look. The numerator, x squared minus 4, is a difference of squares. It factors as x minus 2 times x plus 2. And so when we look at this fraction, we notice that x minus 2 is a factor of the top and the bottom, and therefore it will cancel. And this equality holds, of course, as long as x is not equal to 2. Right? Just because we cancel does not wash away our problems in the denominator from the start. We have to keep in mind that x cannot equal 2 in this function. So our rational function here is really just the line x plus 2, except when x is equal to 2. So what does the graph of this function look like? Well, here are my axes. The line x plus 2 just has a slope of 1 and a y-intercept of 2. But this function has this graph everywhere except for where x is equal to 2. So at the point 2, 4, our graph has a little hole in it. So what we conclude is that this method for finding vertical asymptotes by plugging in problem values in the domain, if we get a non-zero over 0, then we have a vertical asymptote. If we get a 0 over 0, then our function is reducible, and we might very well find that the function has a hole at that x value instead of a vertical asymptote.